Hello everyone, welcome to our second video in solving equilibrium problems. In this video, we are going to look at an example question where I'm going to solve for the equilibrium concentrations when we're given the equilibrium constant. To be able to understand what we're going to be going through in this video, once again, you need to understand the definition of chemical equilibrium, and you need to feel comfortable doing the first set of problems, which is solving for the equilibrium constant given the initial concentrations. So if you haven't done those types of problems or watched that first problem solving video, watch that first, then come back to this one. Let's look at an example problem. In this example, we are looking at the reaction between carbon monoxide and water vapor, and the reaction which produces carbon dioxide and hydrogen gas. In this question, we're given the equilibrium constant at a specific temperature, 700 Kelvin, and we're asked to find all the equilibrium concentrations if we place a certain quantity in a sealed flask. So this is an example of the usefulness of the equilibrium law. We don't have to carry this reaction out and measure things and figure out what's going to be produced. If we know the equilibrium constant and we know how much of each chemical we're putting in, then we can predict how much we're going to get out of the reaction. Once again, this is the value of mathematical formula and mathematical laws in chemistry. It allows us to predict what's going to happen without having to carry out the experiment. Let's go over to the whiteboard and solve this problem. You can start off here by writing a balanced chemical equation and setting up the ICE table. Here's the start of my ICE table. Just like in every example, we start off with a balanced chemical equation. And note that this equation is balanced with a 1-to-1 to 1-to-1 ratio. Next, I've placed my given information under each chemical. And because equilibrium law always involves concentrations, I've converted those values using the concentration equals moles divided by volume, the molarity equation, to solve for the concentrations. And so obviously, if I start with equal numbers of moles in the same sized vessel, we are going to have equal concentrations. I don't necessarily know whether the system is at equilibrium yet, or which way it's going to shift if it needs to move to equilibrium. But that doesn't really matter, because if it's at equilibrium, we will see that the change will be zero when we use our K value. So for right now, and for the sake of argument, let's assume that this equation is going to shift to the right. Maybe I'll just draw a yellow arrow here to envision that. So let's imagine that more reactants are going to be converted into products as this system reaches chemical equilibrium. If that's the case, then that means the substances on the right-hand side are going to increase in quantity or increase in concentration. But we don't know how much, so we're just going to label that value X. Since they're increasing, we're going to place a positive sign there. And the coefficient in front of X is going to match the coefficient in the balanced chemical equation, which is 1. For every 1 carbon dioxide which is produced, we produce 1 hydrogen plus x plus x. For every 1 carbon dioxide which is produced, we consume 1 carbon monoxide. And we consume 1 water. So we don't know the extent of the change. We don't know how big the numerical value is on x, but we do know the ratio in which they change, a 1 to 1 to 1 to 1 ratio. Let's now write these values into our equilibrium concentration, and our equilibrium concentration will be the initial concentration plus the change. Our next step is going to be to solve for x. We can't do anything more here, but we do know the value of k. So let's take these equilibrium concentrations and substitute them into the equilibrium law equation. Here I have my equilibrium law for this reaction. Product of the right-hand side raised to the coefficients in the balanced chemical equation divided by the product of the chemicals on the left-hand side raised to the coefficients there. There are no exponents in this equation because all the coefficients are 1. On the left-hand side, I've substituted the given value for k into the equation. On the right-hand side, I've substituted the values that we calculated in the ICE table for the equilibrium concentrations. Now, you could start solving for x here by expanding and isolating x, but you're pretty soon going to get a quadratic formula, which we want to avoid if possible. So let's do a few algebraic tricks here to simplify this equation. What I have done in the third and fourth line here are some algebraic manipulations here. These are the types of things you have learned in math class. I'm just going to apply them here to simplify this problem. So I recognize that the two terms multiplied both on the numerator and the denominator are the same quantity. So I can simplify that in just writing them squared. If we divide two squares, we can rewrite that as the division and then bring the square to the outside. Since now we have the entire right side squared, we can reverse that operation by taking the square root of the right-hand side. But because this is an equal sign, we have to do the same operation to the left-hand side to maintain the equivalence. I've taken the square root of both sides, and now I'm going to rearrange this equation and solve for x. So now I have a value for x, and x was telling us how much the concentration. Now I have a value for x, and x tells me how much the concentrations changed between the initial and equilibrium points. Let's now substitute the x value in for our equilibrium concentrations. Here are my equilibrium concentrations of all 4 chemical species. Note that because in my ICE chart, the values for the concentrations of carbon monoxide are equal to the concentration of water, I just made them equal here. And same with carbon dioxide and hydrogen gas. That's not necessarily going to be the case. It's just based upon us having a 1 to 1 to 1 to 1 ratio and starting off with equal concentrations. Let's now summarize the steps we used to solve this problem. And as you can see, the first several steps are the same. We made sure we had a balanced chemical equation. And below that equation, we created an ICE table. We looked at the given quantities, and if needed, we converted them into concentrations. And then we took those values and placed them into the ICE table. Next, we had to write in those values of x, which were the change values. We got those values from the mole ratio, remembering that if one side of the equation is increasing, the other side is decreasing. We found our equilibrium concentrations that involved x, and we substituted those into the equilibrium law equation. Since we were given the value of k, we then solved for x. In this case, we used the fact that we had perfect squares on the right-hand side to simplify by taking the square root of both sides and then solving for x. Finally, we remembered that x was not the value that we're trying to find. X wasn't unknown, but the question asked for the equilibrium concentrations. So I used the value of x to solve for the equilibrium concentrations. And this last step here is often one that students forget, especially in long questions where there's a lot of steps. You get the value of x, and you think back to math, okay, I solved for x. Well, x was an unknown, but it's not what we were asking for. So always refer back to the question and make sure what you're answering is the question that was asked.